Hi, my name's Matt Wilchek. My partners are Alex Tsai and Kristen Bradley, and our project is called Attacking and Defending Object Detection Software for AI-Assisted Driving. Next slide, Alex. So we're going to go through what our project's about, some related research around the concepts, what we did for an offense implementation, and then a defense implementation. And then we actually integrated these two concepts and created a really great simulation tool where we can experiment in our offense and defense concepts and implementations. And we'll actually show a really great demo that shows these concepts working together. And then we'll go through some of the limitations of the research and work, some future research concepts that could be extended from what we've done, followed by a conclusion. Next slide. So artificial intelligence object detection software has becoming increasingly common in automobiles, allowing for features such as lane departure, warnings, and automatic emergency braking. Many cars today come equipped with new sensors and cameras that make these features possible. And so as cars drive about the road, the cameras and sensors are constantly capturing new images that are inputted for inference to the AI software. And when a detection is made, it can be visualized with a bounding box around the object, along with a label and a confidence value. So in our slide, figure 1 and figure 2, these are just one of many examples of a typical context in an AI assisting driving software that would be expected to perform. We have a scene where a car is maybe stopped behind another car at an intersection. And if the car had AI assisted driving software, this would be the kind of visualization that a user would see if we wanted to see what the software was analyzing. So, for example, in the first picture, we would see a big bounding box around the car. The computer would understand where the traffic lights are and any other objects that would be important. You know, in figure 2, we have now an intersection with people, right? And so the software is able to pick up when people are crossing the road. So this research has shown that these systems, however, can be vulnerable to attacks, which could compromise the safety of both drivers and pedestrians. A study published in 2020 by researchers at Purdue University actually found that the object detection systems in autonomous vehicles can be easily fooled by simple yet effective attacks, such as adding stickers to road signs or changing the color of traffic lights. And so these attacks are also known as adversarial machine learning, and can cause the AI system to misinterpret the environment, potentially leading to a dangerous driving decision. In our paper that we are submitting for our final project, we discuss some of the latest research in offensive attacks toward object detection and defensive methods that can be used to deter them. We detail a simple offensive method that can be used to attack common object detection software, and a detailed implementation of a defensive method that can be used to defend the attack. We then integrate our offensive and defensive methods into a simulation tool that can be used to generate a number of scenarios that demonstrate the success of each method that will be demoed later. Next slide. So one of the most common types of adversarial attacks on object detection is perturbation attacks. And this is where attackers can inject varying frequencies of noise into the input image right before inference to deceive the object detector. Many studies have explored different methods to generate perturbations, such as fast gradient sign method, projected gradient descent, and Carlini and Wagner attacks. Some of these methods actually can mislead the AI model into detecting objects in the wrong locations or with incorrect sizes. Another type of adversarial attack is evasion attacks, where attackers can modify the input images to make the detector completely fail to detect the objects correctly. And actually, since 2014, researchers have demonstrated that small perturbations to input images can cause object detection models to misclassify them with a high confidence value. So for example, in figures 3 and 4 below, we can see varying degrees of motion blur is added to a picture. And when the image is passed to the object detection model, it actually begins to misclassify as a person or a boat to eventually no detection at all. So transferability is an essential property of adversarial examples, and it has been the latest area of recent research for attacks on object detection. One pre-trained attack can actually determine the effectiveness of an attack on different AI models. Recent studies have actually shown that adversarial examples generated for one model can often transfer to other models, even if they are trained on different data sets or model architectures. And so by exploring transferability, attackers can target multiple models with a single set of adversarial examples, making their attacks more efficient and effective. Next slide, Kristen.
And now for some defense-related research. Available object detection defenses are growing in number, and a few defense methods include adversarial training, gradient masking, and input modification. Adversarial training intentionally involves training a model with both clean and adversarial examples. After the initial training phase, the model is retrained using the same adversarial data, but with the correct labels manually assigned. While this method is generally effective, it is not flawless. This method may suffer from overfitting and overgeneralization. Next, gradient masking is a method of obfuscating the gradient of a model. The gradient describes how the output of the detection function changes as its input parameters change. In 2015, researchers believed that defensive distillation would be an effective defense against adversarial inputs. This technique involves training one model on the output generated by another model, which is considered more resilient to attacks than the original data. However, researchers from UC Berkeley proved this defense method ineffective later that same year. The primary issue with gradient masking in general is that attack inputs are transferable between models. Therefore, an attacker can either build or find a similar model, successfully attack the secondary model, and then apply the adversarial inputs to the initial model. Finally, input modification is a technique used to remove as much noise as possible from a potentially adversarial input. We focus on this in the defense approach. The choice of input modification technique depends on the type of adversarial attack used against the model. For instance, one technique is to denoise an image, which can increase the probability of an accurate prediction. However, denoisers can suffer from the error amplification effect, in which small residual adversarial noise is progressively amplified and leads to wrong classifications. And now on to our different implementations. Next slide, please.
So for our offense implementation, as mentioned in our related research, perturbation attacks are one of the most common types of methods used against object detection software. And after reading about a recent and novel successful method called poltergeist, used as an evasion attack, we decided to apply a similar method that allows the attacker to pick varying degrees of noise and blurriness before inference by primarily using two key math equations in our attack algorithm. The first one, the Gaussian blur, is a popular technique used to smooth images and reduce noise. It works by applying a Gaussian function to each pixel in the image, where the function's standard deviation determines the amount of blur applied. However, instead of reducing blurriness in an image, we are applying the Gaussian blur to create specific degrees of blurriness to an image for specific desired outcomes. So, to apply the Gaussian blur, let's break down the first formula that we have. The first equation is applied in multiple iterations over the same image, or a convolution. The convolution operation involves sliding a kernel, which is a small matrix that contains the Gaussian function values, over the image. The kernel's size and standard deviation determine the amount of blur applied. The gxy is the value of the Gaussian function at the pixel coordinates of x and y for the image, while the sigma is the standard deviation of the Gaussian function, which determines the amount of blur applied. Speckle was the second equation that we used, which created another type of interference caused by the presence of random noise in an image. Speckle results in a pattern of bright and dark spots that appear randomly scattered throughout the image. Speckle is common in ultrasound and radar imaging, where it can be caused by the reflection of waves from rough surfaces or irregularities in the medium being imaged. There are several speckle methods that are actually commonly used in image processing, including the Rayleigh, gamma, and log normal models, but for our algorithm, we implemented Rayleigh. Looking at our second equation, the affected image is represented by IXY. AXY is the underlying image intensity, and ZXY is the random variable representing the speckle interference. The Rayleigh speckle method assumes that ZXY is a Rayleigh distributed random variable with a probability density function. To actually add the Rayleigh speckle perturbation into an image, we first generate a random noise value for ZXY. In order to create our desired outcomes, we next had to conduct several experiments of varying values for both the Gaussian blur and speckle methods. Let's look at some of these examples next. Next slide. So after applying our perturbation attacks to the image, we then passed it to a pre-trained YOLO v5 model for object detection inference. As added context, we tested our method on images commonly inferred for AI-assisted driving, such as a car stopping at a red light with another car or pedestrian in front of it. As a note, these figures do come from our final research paper that we plan to submit for this project. So looking at our Gaussian blur tests and starting at figure 3, we have a standard deviation, or SD, of 100. And the detection result from the AI model actually fails to detect all of the traffic lights, but still detects the cars. In figure 7, with a standard deviation of 160, the AI model now misclassified the car as a truck, but with only a 44% confidence. And it's not until figure 9, with a standard deviation of 195, that the AI model now fails to detect anything in the image. And so this is the standard deviation value that we decided to keep for our final offense implementation. Now, if we look at our speckle tests, we started the experiments off with a relatively high sigma value of 1.5. The AI model detects the important objects in the scene except for a couple of traffic lights in figure 12. By only slightly increasing the sigma value to 1.8, the AI model not only fails to detect the traffic lights, but is now completely misclassifying the large car as a suitcase in figure 14. Our final test with a sigma value of 2, which resulted in our ideal case of no detections at all in figure 16. Therefore, for our final offense implementation, we kept our sigma value equal to 2 for our speckle method. Next, Kristen will discuss how she defended these attacks using our resulting tampered images to attempt to turn back to normal for expected detections. Next slide.
The criteria for our defense implementation is to defend against both Gaussian and speckle noise attacks. Since we are constrained on time and compute resources, we implemented an input modification defense approach as opposed to adversarial training or gradient masking. Additionally, we need to preserve as much detail as possible when denoising the image so that our model can correctly identify objects within the input image. We begin by applying a Gaussian filter to the input image, which performs initial smoothing based on a given sigma value. We chose a small sigma value of 0.8 to apply mild smoothing to the image without significant loss of details. Next, we apply a bilateral filter to the input image. The bilateral filter replaces each pixel's intensity value in the image with a weighted average of the intensities of nearby pixels. The filter then groups pixels that are spatially close and have similar intensities, which means those pixels are more likely to belong to the same object in the image. Thus, the bilateral filter does well to preserve key details. This approach is an effective secondary denoising step against both Gaussian and speckle noise as it averages out the current noise in total. However, because this filter is computationally expensive, we choose to only apply it once over a given image. Lastly, to reduce the noise in the image while preserving its edges and sharp features, we employ total variation, or TV, denoising based on the Chambol algorithm. This algorithm works by minimizing the total variation of the image subject to a constraint on the fidelity of the original noisy image. In other words, the algorithm attempts to smooth the image while ensuring that the denoised image remains faithful to the original noisy image. The result is an image with reduced noise that retains its important details. Because the Chambol algorithm was designed to be efficient and iterative, we choose to apply TV denoising to an input image 5 times. This amount appears to achieve a usable balance between reducing noise and preserving key details. Next slide, please. On this slide, we have an example of a before and after image of our defensive process. On the left side of the figure, we have an image that we inflicted with Gaussian noise. The image on the right is the noisy image after it has been processed through the defense script. Notably, as a result of our defense, our model not only detects an additional car in the defended image, but also shows an increased confidence detecting the other vehicles in the image. Next slide, please. Here we present another before and after example. The figure shown in this slide demonstrates the difference in object detection before and after defending an image from a speckle noise attack. On the left side of the figure, we can see that the speckle noise has not only removed the model's ability to detect most of the objects in the image, but the model has also misclassified a car as a suitcase. Meanwhile, the right side of the figure shows that our defense allows the model to correctly identify several items in the image, including the originally misclassified car. And now we'll move on to how we implemented our simulation, thanks to Alex. Next slide, please.
So our system utilized Next.js, a React-based framework for front-end development, which offers numerous advantages such as client-side optimization, easy routing, and automatic code splitting. We have 4 main pages in our front end, which is home, attack, defense, and the right-hand side, the review page. As for the backend part, we employ the Python Flask framework, a simple, flexible framework for developing RESTful API. To handle a synchronized task, we use Celery, a powerful task queue library supported by the Redis, and in-memory data store for the task queue and metadata management. The backend workflow include the image upload, asynchronous processing, and handle the text ID and the image URL. So when the backend servers receive the job from the front-end server, and according to different requests, it will delegate to attack simulation or defense simulation. And after the queue is launching, the right-hand side will showcase how it works and log everything in the backend part. So our system architecture is mainly focused on the seamless front-end and back-end communication through the RESTful API and task queue, ensure a responsive user experience. The review of the subpage allows users to compare the original and modified image. So the left-hand side is a total system architecture, how the data flow works from the user request to the backend job delegation, job allocation part. Okay, so let's go into the demo part. So here's the website I just mentioned in the previous slides. So the attack function is really simple. We just have to upload the image, original image. So, okay. So I'll pick the picture from the, for example, for the first example, we use like a car image to upload it, and then when you press the upload function, it will trigger the backend part to delegate the attack function. After the few minutes, it will show the noise, the noise picture in here, and you can download it. Yeah, here. Okay, let's go through the defend part. So like in the defend part, it's a similar logic. We just have to like upload the similar upload the attack image. So for example, this is a noisy Gaussian result attack image from here, and we upload it. Okay. And similar, it will launch the backend. The backend will run the jobs asynchronously. And then after finish the work, it will upload to the modify image section. And you can see, here's the defense. Here's the process of defense mechanism works. And then you still can.
Sorry, let me cut in here real quick also, Alex, to help add to what you said. But we actually have an AI model running for both the attack and the defense implementations on this website. On the attack subpage, when we actually upload the image, an AI model is actually being used to try and detect the scene. However, the image gets tampered with from our Gaussian and speckle math equations on the image, which result in that image with no detections. And then same with the defense, where the model is still being used on the tampered image, but thanks to Kristen's algorithm, she's able to smooth things over where the model actually works and detects things. Yeah, pick that one. Save that as a picture in your downloads. And let's use that picture for our simulation. So in the attack, you can pick that, boom, upload. The model's going to run on it. Oh yeah, see? So we added a bunch of Gaussian blur and speckle attacks to it. The model didn't detect anything because we don't have any bounding boxes. So let's download it. Let's download that tampered image and then upload that tampered image to the defense tab. And let's see if Kristen's magic works again. There we go. Okay, hey, we got a car and a stop sign this time. That means we got detected objects. The AI driving assisting software will realize, hey, there's objects in front of me. I should probably stop. Mission saved. Okay,
yeah.
I'll let you take the rest.
Yeah, so that's a whole demonstration about our system. Like we discovered for like 3 pages, and each pages, when you upload the things, the backend servers will delegate the process to the backend servers, and using like a job queue to like a.
Hey Alex, let's do a second demo for fun. Go to the attack page. Okay, great. Actually, go back for a moment. Go bring up another tab in your web browser. Go to Google, and yeah, type in car stop. Actually, you already have something kind of pulled up interesting. Car stop, and yeah, that's fine. So I guess you're looking at that. Yeah. So let's go. You see that hit and run accident at an intersection?
To serve the backend service. Yeah. So that's the whole logic about our system.
Alex.
Okay. So let's talk about the limitation part of the previous works. So AML attacks have several technical limitations. Adversarial training, while generally effective, can suffer from overfitting and overgeneralization. Gradient masking part has the issue of transferable attack input between models, allowing the attacker to exploit the secondary model input modification, as reported by the previous work, can result in the error amplification effect, where residential adversarial noise is amplified, leading to the incorrect classification. Apart from technical limitation, AML attack face other challenges, such as evasion attack. Evasion attacks are time and resource intensive, which can limit the large-scale attack. Adversarial example may not always full human perspective, as human may see through the manipulation, detection, and defense mechanism against AML attack are continuously evolving, require attacker to constantly adapt and invest resources to develop a new and more effective attack module. Sorry, let's get through it. So in the future research part, the robot feature extraction can be achieved by examining novel neural network architecture like CNNs and RNNs, or employ alternative feature extraction methods such as Gobert feature or wave transform. As for the dimension limited optimization, can help reduce the number of label pixels without sacrificing the descriptive power while maintaining the robustness to small precipitation in the input data. So as for the enhanced system resilience, adversarial training can be employed by adding tricky example to the training process. Homomorphic encryption can also help to prevent adversarial model attacks by enabling the computation on encrypted data without exposing the sensitive information. Lastly, by using the example AI, a decision making can be made more transparent, enabling scientists to find it and fix weak spot in the object detection system, protecting them from the harmful attacks. Let's talk about the conclusion part. So in conclusion, this study has demonstrated the vulnerability of object detection software AI assists automobile to adversarial attacks, and shows that such system can be made more robust to such attack. While our attack and defense methods are not novel, our findings have contributed to ongoing the discussion on the importance of handling AI classification and image processing in the development of a secure and reliable AI assist automobile. However, it is important to acknowledge the constraint and limitation of our study, such uses limited data set and potential insufficient of our defense against more sophisticated attack. Future research can build upon our finding by exploring novel attack and defense methods and testing their performance on large and more diverse data sets. Overall, this study underscored the need for the continuing research and development of more robust and secure object detection software AI assist automobile, which are essential in ensuring the safety and reliability of such systems.